Another big topic in the world of inference is the topic of hypothesis tests. And we're going to start off talking about hypothesis test for a proportion. Suppose someone makes a claim and we want to verify whether the claim is true. For example, Cal Poly Pomona claims that 15% of all students live on campus. How can we verify that? We could talk to the entire population of students, but that would be very time consuming. We would like to be able to examine a sample from the population and determine from that if the claim is true. So suppose we select a random sample of 200 Cal Poly Pomona students and we find that only 19 of them live on campus. That's less than 10%. So the question is, how likely is it to have observed a sample proportion like this, less than 10%, if Cal Poly Pomona's claim is actually true? So when we say a sample proportion like this, we mean a sample where only 9.5% live on campus. The 19 out of 200 is 9.5%. And when we say a sample proportion like this or worse, we mean getting a sample proportion this far away from the mean or farther. This far away from the mean or farther. In this case, that would mean getting a sample with a proportion living on campus of 9.5% or lower, like we did, or 20.5% or higher. 20.5% is just as far away from 15% as 9.5% is. And when we say how likely it is, we mean to determine the probability of this happening. And we're going to assume for a moment that the Cal Poly Pomona's claim of 15% is true, kind of like someone who is in court innocent until proven guilty. So, what we know about the sampling distribution of p hat. The mean of the p hats is the population p, which is 0.15 according to the claim. The standard deviation of the p hats is radical p times 1 minus p over n, which is 0.02525, assuming that the claim of 15% is correct. And the p hats are approximately normal because n times the claimed population p and n times 1 minus the claimed population p, both of those are greater than or equal to 10. And remember, we had a z-score formula also for turning a value of p hat into a z-score. So the p hat of 9.5% or 0.95, we turn that into a z-score. And the other p hat going the other direction, this is not from our sample, but remember 20.5% is just as far away from 15% as 9.5% is. So we turn that into a z-score, that's positive 2.18. The probability of a p hat less than 0.95, which is the probability of a z less than negative 2.18, is 0.146. And greater than 20.5% is also 0.146. So the probability of observing a sample proportion as extreme as the one we observed, or worse in either direction, so this far away from the population, the claimed population proportion, or more in either direction, the probability of that happening is 0.292, which is just the sum of those two. And notice, because of the symmetry of the normal curve, we could have just done one of these calculations and multiplied by 2. Anyways, this probability of 0.0292 is referred to as our p-value. It's the probability of observing what we actually observed, or worse, if the null hypothesis is true. This is a fairly small probability. In other words, there's less than a 3% chance that we would get a sample this extreme if the claim was true. So we have to make a decision. Is the claim actually true and we just got a strange sample? Or is the claim false and we got the sample that we got because the population p is actually something other than 0.15? This decision of which one of these we choose up here is usually made by comparing the calculated p-value, 0.292, to a number the statisticians call significance level, which is usually indicated with the Greek letter alpha. Most of the time we'll be using an alpha of 0.05, but oftentimes a problem will state, is this result significant at alpha equals some number. So sometimes they'll give us an alpha of 0.05, sometimes it'll be an alpha of 0.01, sometimes alpha is 0.001, but if it's not otherwise stated, we're going to use an alpha of 0.05. Since our p-value is smaller than alpha of 0.05, we conclude that a result like this is very likely to have happened by chance, and thus it provides strong evidence that the claim is not true. And very key note here that a lot of students get backwards. Small p-value means we have strong evidence against the claim. The entire process of testing a claim is referred to as a hypothesis test and is usually formally carried out in 4 steps. First of all, write a pair of hypotheses, then collect evidence, then determine the strength of that evidence, which is our p-value, and then make a decision based on the strength of the evidence. So, by the way, this 4-step process often on a free response problem often turns into a part A, part B, part C, part D. So, for example, on this example we've been working with, the hypotheses would look like this. The null hypothesis, H subscript 0, is the population P is 0.15. That was the claim made by Cal Poly Pomona. That's what we are going to, for the moment, we're going to assume that that is true. The alternative hypothesis, H subscript A, is that the population P is not equal to 0.15, where the population P we're talking about is the population proportion of all Cal Poly Pomona students who live on campus. This H subscript A is sometimes written as H subscript 1. So, what evidence do we have that the population P might be not equal to 15? Well, we have our P hat. 19 out of the 200 that we surveyed are living on campus, which is 9.5%. Sample size is 200. So we turn that into a z-score. We get a z-score of negative 2.18. This 0.095 is from our sample, so that's sometimes referred to as the test statistic. Then we turn that into a z-score. This is sometimes referred to as a standardized test statistic, although some books just call this final z the test statistic. So now we determine the strength of the evidence by finding the probability of such a z-score. And after multiplying by 2, we get this. This is called our p-value, the probability of observing what we observed or worse if the claim is true. And then we have to make a decision based on that p-value. Because the p-value is so small, and again, the dividing line for what is referred to as small is the significance level alpha, which we said for this problem we're going to do an alpha of 0.05. Because the p-value is so small, how small? It's less than 0.05. We reject H naught. We reject the null hypothesis. We have strong evidence the true population proportion of all Cal Poly Pomona students living on campus is not 15%. And when we make this decision, there's only 2 possible decisions we can make. We either reject the null hypothesis or we fail to reject. Just like in a court of law, the final decision is either guilty or not guilty. And the decision should always be based on the size of the p-value, and the decision should always be stated in context. Now, some variations on that. Suppose we had gotten a little bit different p-hat. Suppose our sample of 200 students had resulted in 24 of them living on campus. Then our test would have looked like this. I'm streamlining the test a little bit. Null hypotheses are exactly the same. The evidence is now 0.12 for p-hat, which now turns into a z-score of negative 1.19. the probability of a z-score less than negative 1.19 is about 0.11. Double that and you get about 0.22 or 0.23. That's our p-value. And now the p-value is large. Why do we say large? Because this p-value is greater than 0.05. So in that case, we fail to reject H0. We do not have enough evidence that the true population proportion of all Cal Poly Pomona students living on campus is not 15%. Notice that failing to reject H0 is not the same as accepting H0. Again, at the end of a trial, someone is either guilty or not guilty. They don't say innocent at the end of the trial. It's either guilty or not guilty. Either guilty or we don't have enough evidence to say that they're guilty. So in this case, just because we have decided that we're going to fail to reject H0, we did get a p-hat that is not equal to the claim of 15%. So even though we failed to reject H0, that doesn't mean that we've proven H0 is true. We just don't have strong enough evidence to say that it's false. Okay, here's another variation, one-tailed test versus two-tailed test. So now look at this example. Suppose we initially had some suspicion that the proportion of students living on campus is less than 15%. And suppose the sample we gathered was the same, 19 out of 200. Now notice that our alternative hypothesis is p less than 15%. We're trying to see if we have evidence that p is less than 15% based on the suspicion going in. We collect evidence and turn it into a z-score as before. We determine the strength of the evidence, same z-score leading to the same probability, except now we're not going to multiply that probability by 2. Our p-value is 0.014. And then in the decision phase, we are once again comparing that p-value to some cutoff like 0.05. And since it's smaller than 0.05, our decision is reject H0, which means we have strong evidence that the true population proportion of all Cal Poly Pomona students living on campus is less than 15%. Notice this statement here, less than 15%, that fits with our alternative hypothesis, which was less than 15%. All of this that we've been doing is referred to as the p-value approach, calculating the probability that we observe a sample as bad as this one or worse, and then make a decision based on that probability. But another approach is to determine ahead of time what magic z-score would lead one to reject the null hypothesis. And then once you figure out the z-score for your sample, we'll know whether to reject or fail to reject. For example, in example 1 and example 2, both were two-tailed tests. If we know that our significance level is 0.05, that means 2.5%, half of the 0.05 in each tail. The z-score that leaves 2.5% in the left tail is negative 1.96, and the z-score that leaves 2.5% of the right tail is positive 1.96. So as soon as we get the z-score that's less than negative 1.96, remember we got a negative 2.18 on example 1, or if we had gotten a z-score greater than positive 1.96, we already know we should reject H0 because we know the p-value will be less than 0.05. If we get a z-score that's between negative 1.96 and positive 1.96, then we know we're going to fail to reject H0 because the p-value would be greater than 0.05. So that's referred to as the critical value approach, determining ahead of time what value of z would cause you to reject the null hypothesis, and then compare z to that magic value of z, as opposed to calculating a probability and comparing that probability to 0.05. How we determine this z of negative 1.96 and positive 1.96 is very similar to how we find a z star for constructing a confidence interval, which is also called a critical value. This is kind of an old school technique, which is a carryover from the days when we did not have technology in our hands that would calculate the probabilities very easily. And even if the textbook does not refer to the critical value approach. You still might hear the phrase rejection region, which would refer to this shaded area here on a two-tailed test, or this shaded area here on a one-tailed test. If we were doing a one-tailed test like in example 3, we need the magic value of z that leaves 0.05 in the tail. Looking at the table, you'll see that that's a z-score of about negative 1.64 or negative 1.65, and often negative 1.645 is used for that. Then the final topic we need to talk about here is error types and power. So whenever we make a decision about the population and we don't have complete information because our decision is being made based on a sample, we sometimes make the wrong decision. Sometimes H0 is true, but we get a little bit of a goofy sample that causes us to reject H0. When we reject H0, even though H0 is true, this is referred to as a type 1 error. Sometimes H0 will be false, and just by chance, we get a strange sample that causes us to fail to reject H0. And when we fail to reject H0, even though H0 is false, this is referred to as a type 2 error. This is often summarized in books in a table that looks something like this. The reality of the situation is either H0 is true or H0 is false. The decision we make is we either reject H0 or we fail to reject H0. If H0 is true and we reject it, that's an error. If H0 is true and we fail to reject it, that's a correct decision. If H0 is false and we reject it, that's a correct decision. If H0 is false and we fail to reject it, that's a type 2 error. These errors have probabilities associated with them. The probability of a type 1 error is simply alpha, whatever our significance level is. So if alpha is 0.05, then you're going to wrongly reject H0 about 5% of the time, because about 5% of the time you will get a goofy sample that will cause you to reject the null hypothesis. The probability of a type 2 error is called beta, and I'm only including this just for completeness. We don't actually talk about how to calculate beta in this class, but just so that you know that one error type is referred to as alpha and the other one is referred to as beta. The reason why it's difficult to calculate beta is because beta depends on how far wrong the null hypothesis is. If the null hypothesis is wrong, but not by much, then there's a large probability that you would fail to reject the null hypothesis. But if the null hypothesis is wrong by a lot, like let's say there was actually only 8% of students living on campus, then we would hardly ever get a value of p hat close to 15%. So we would hardly ever fail to reject H0, and beta would be close to 0. Closely related to beta is something called power, which is the complement of beta. So remember, type 2 error is when we fail to reject H0, even though H0 is false. The complement of that is what we would like to do. We would like to reject H0 when H0 is false. And the probability that we do that is called power. So power is technically the probability of rejecting the null hypothesis given that the null hypothesis is false. And that's 1 minus beta. And like beta, power can be difficult to calculate. Power is also referred to as the power of the test. It can be difficult to calculate because it depends on how far wrong H0 is. And I said a lot here in words, but let me show you this is a simulation of our Cal Poly Pomona living on campus example. If we have an alpha of 0.05, well, here's our sample. We have a sample of 200 students, and each of those students either lives on campus or they don't. Live on campus is determined by ones, and not live on campus is zeros. And these are supposed to be happening 15% of the time, if the claim is true that 15% of people live on campus. So if the population proportion really is 15, notice that we're still rejecting the null hypothesis, in this case 59 times out of 1,000. So about 5 or 6% of the time. So let's scroll over to here. This is the first example. So this example here, we happened to get 40 students living on campus, which gave us a p-hat of 0.2, which gave us a z of 1.98, which led to a very small p-value, a p-value that was smaller than 0.05, so we reject. But that doesn't happen very often. In fact, it should only happen 5% of the time. If I redo the randomization, now the probability of a type 1 error is 0.06, 0.05. So again, the probability of a type 1 error is basically turning out to be what alpha is. If I change alpha to 0.1, notice that now I'm rejecting the null hypothesis almost 10% of the time. Okay, so again, the probability of a type 1 error is basically going to be alpha. Let me change this one more time down to 0.01. So with an alpha of 0.01, we are usually rejecting the null hypothesis 1% of the time. Okay. Now, what if the population proportion isn't 0.15? What if the proportion of students living on campus is really 0.14? Well, you notice that 0.14 is so close to 0.15 that I'm still only rejecting the null hypothesis 5% of the time. Okay, now 7% of the time, 6% of the time. So I'm not very often rejecting the null hypothesis because 0.14 is really close to 0.15. So the power of my test, the probability that we would reject the null hypothesis when p is really 0.14 is about 7%. But if the reality is more wrong, if the proportion living on campus is like 9%, then we will often reject the null hypothesis. It looks like we're rejecting the null hypothesis about 75% of the time. Sometimes, about 25% of the time, we're making a type 2 error, meaning sometimes we fail to reject, even though the null hypothesis is false, 0.09. And again, the more false the null hypothesis is, let me change it to 0.08, the more false the null hypothesis is, the greater our power. So that's a little bit of an illustration of power and type 1 error and type 2 error. So that wraps up the first phase of hypothesis tests. This was hypothesis test for a population proportion. Next up is hypothesis test for a population mean.